with a mass of 0.360 kg is dropped from
kg.
kilograms.
Thank you. Sorry, I don't like to use just say the letters. It's better to say what they are.
Alright, is dropped from a height of 1.20 meters above the top of a fixed vertical spring. The spring constant is 350 newtons over meters. What is the speed of the ball when the spring has been compressed 5.00 centimeters?
So we're dropping the ball from a height of 2.0 meters above the spring. The spring is then compressed by the ball by a distance of 5.00 centimeters. And the question is, what is the speed of the ball when it has compressed the spring by 5.00 centimeters? Is mechanical energy conserved in this particular problem, Sean?
Yes.
You know this because? But the goal here is to be able to answer that question when it comes to a final exam, and at which point you won't actually know, clearly this has a mechanical energy problem. I agree with that. But on the final exam, you won't know that. So what is it about this problem that says mechanical energy is conserved? Goolsby.
The ball is going through the vacuum you can breathe.
The ball is going through flying through the vacuum that you can breathe, and there is therefore no friction. So we know mechanical energy initial equals mechanical energy final. Conservation of mechanical energy. We list all three of the types: kinetic energy initial plus gravitational potential energy initial plus the elastic potential energy initial equals the kinetic energy final plus the gravitational potential energy final plus the elastic potential energy final. We get the equations: 1/2 mass times velocity initial squared plus mgh initial plus 1/2 kx initial squared equals 1/2 mv final squared plus mgh final plus 1/2 kx final squared. Before we can move on, before we can use this equation, Claire, what do we need to do?
We need to cancel out some stuff.
We can't cancel out stuff yet because we don't even know how we would know what to cancel out. So we cannot do that yet. Before we can do that, we must first, Jack.
Split it into 2 parts.
I agree with that, but more specifically, I need to do what, Edward?
Initial, final, and
We need to identify the different points, right? We need to identify the initial point, the final point, and as you said, the zero line. So let's start with initial and final points. Aaron, what are good initial and final points?
Well, when you look at this for the spring, or do you look at the compression of the spring for the initial and final point? So the initial point would be where the spring is not compressed,
Okay, so initially all the way up here.
and then the final point would be when it's compressed.
Okay, and the final point we'll put where it's compressed. Some of you want to put this as your final point, which is right before the ball runs into the spring, which is fine. Energy is conserved all the way to here, and then you want to do another one, an initial and a final from here to here, which is fine. You could do it that way, but that's extra work. Energy is conserved all the way throughout, so there's no reason to do an intermediate step, which is to find the velocity right before this object strikes the spring. We can go all the way from the very top until it's compressed by 5 centimeters. Adam.
Okay, so when it hits the spring, wouldn't that slow the ball down?
It does slow the ball down, and you'll see that in the conservation of mechanical energy.
So how is energy conserved if it slows down?
Okay, how is energy conserved if it slows down? Fair question. Goolsby.
It's going into elastic potential energy.
It's becoming elastic potential energy. It becomes energy stored in the spring. All right, so we have our initial final points. We need our zero line. What's a good zero line, please? Carolyn.
At the top of the not compressed spring.
So right along this dotted line right here. Okay. This is a fine spot to put the zero line. We can put it right there. Okay. Now we can start crossing things off. Please give me something we can cross off. Danner.
Velocity initial,
is
0.
0. So the velocity initial is equal to 0, so we can get rid of the kinetic energy initial. What else can we cross off, please? Carol?
The potential spring energy is 0 in the beginning
In the beginning, why?
because the spring isn't compressed.
The initial compression of the spring is 0, so we end up with the 1/2 k x initial squared canceling. So we're left with mgh initial equals 1/2 mv final squared plus mgh final plus 1/2 k x final squared. Class, what did everyone bring to the party?
No.
Nothing. Sadly, the answer is nothing. 1/2 kx final squared doesn't have mass, so there's nothing throughout. It's a sad moment, but we cannot have a dance party. Okay, so we now need to solve for the velocity final. We can multiply through by 2. Let's do this all with letters because that's a lot more fun. We get 2 mgh initial equals mv final squared plus 2 mgh final plus kx final squared. Our goal is to solve for velocity final, so let's subtract 2 mgh final and kx final squared from both sides. We get 2 mgh initial equals, minus 2 mgh final minus kx final squared is equal to mass times velocity final squared. Bring that up here. Solve for the velocity final squared is going to be equal to 2 mgh initial minus 2 mgh final minus kx final squared. All of that divided by the mass. And then we need to take the square root in order to solve for velocity final. We get velocity final equals that whole mess. We now need all of the variables here. Mr. Reed, 2 times the mass
0.36,
times the acceleration of gravity here on planet Earth.
9.8,
Positive or negative?
positive.
Good. Height initial? So the initial height above the 0 line.
1.2,
1.2 minus 2 times the mass, which is 0.36. You already told me the acceleration of gravity 9.8. The height final.
negative 0.05,
Negative 0.05. Where's that number coming from?
because it's compressed 5
5 centimeters. So we need the 5 centimeters in meters. Centimeters cancel out, and we end up with 0.05 meters. Sure. Why negative, Mr. Reed?
because it's below the 0 line.
Good. It's below the 0 line. Minus k,
350,
350 times x final.
negative 0.05,
Negative 0.05, and that is squared, divided by the mass,
0.36,
0.36. And we take the square root of the whole thing.
Oh, 4.6978 meters.
With sig figs, 4.70 meters per second is the final speed. How would things have been different if instead of setting the 0 line here, we set the 0 line at the location where the spring is compressed by 5 centimeters? Adam?
We could have canceled out equations with H final.
The gravitational potential energy final would be 0. What other variable would be different? Because something else would need to be different as well in order to make it so that we get the same answer. What else would be different?
The
Juliana?
height initial.
Would be
1.2 plus 0.05.
0.05, but yes. So notice the height initial then would be the 1.2 plus the 0.05 centimeters or 1.25 meters. And in the end, you'll get the exact same thing. It's just that you set your 0 line at a slightly different location, so the math ends up being slightly different, but gets you the same